it's a bit of a far right kind of comment, but we designed a brake system for a NASCAR where they go on the ovals and they're kind of running always in the same direction. And they ran a different brake package on the left to the right of the car. So they ran different piston areas on the left-hand side to the right-hand side on the rear so that when you hit the brakes, it helped with turning.
Welcome to the HPA Tuned In podcast. I'm Andre, your host, and in this episode, we're joined by Steve Hodgkins from Alcon in the UK. Alcon probably shouldn't need too much of an introduction, one of the big name manufacturers of braking components, among others, but we are really focusing on the braking side of their business today. And braking is one of those elements of any performance car that is easy to overlook. And when we start getting down into the nitty gritty, it is actually quite a complex area and there's a lot to understand, which is why we're joined by Steve today. This podcast episode is going to be perfect for anyone wanting a better understanding of their braking system, the components involved, the manufacturing techniques, and all of the other little idiosyncrasies, such as how we should best bed the brakes and what we're actually even trying to do with the bedding process. Why is a monoblock caliper better and more expensive than a conventional two-piece caliper construction? Why do calipers have differential size bores? Just scratching the surface on some of the topics we chat to Steve about. Before we jump into our interview though, for those who are new to the HPA Tune In podcast, High Performance Academy is an online training school. We specialize in teaching people how to tune EFI, how to construct reliable quality wiring harnesses, how to build your own performance engines. We also cover race driver education, race car setup and fabrication. You can find our full course library at hpacademy.com/courses, and as a podcast listener you can also use the coupon code podcast75. That'll get you $75 off the purchase of your very first HPA course. Worth mentioning, all of our courses are delivered via online video modules so you can learn from the comfort of your own place and you can learn at your own pace. We'll put a link in the description to that coupon code as well as a link to our courses. All right, enough with our introduction. Let's get into our chat with Steve now. All right, welcome to the podcast, Steve. Thanks for joining us today. And as always, we're going to start by finding out a little bit about your background. How did you get interested in cars in the first place?
Yeah, thanks, Andre. So yeah, I probably got interested in cars as most people do as an early age, probably passed down from kind of parents who were kind of interested in it as well. Interestingly, my dad used to be a test engineer for one of the big tractor firms. So kind of mechanical, taking things apart, understanding how they worked was always an interest. So that certainly got me into the car side of things. And I started building a car of my own from the age of about 17. Before I even got my license, I started building my first car. So yeah, when finally I got my license, then
you were good to go.
Good to go, yeah, exactly. So yeah, I think that got me interested in the whole car side of things and set me on a path really kind of education-wise that was focused around engineering. Probably not really knowing at that point how I was going to apply that engineering. Yeah, I was actually at university up at Sheffield, came back home one weekend, and I can't remember, somebody said, oh, there's a job going just down the road at a company that makes brakes for race cars. So I kind of applied for the job, got an interview, and within a week I'd quit the university course I was on, started work at Alcon and signed myself up to night courses to continue the education.
So you're literally straight in the deep end.
Yeah, for sure. And it was a small team of people. Alcon was, 30, 40 people back then. And we'd got, 2 design engineers. We had more drawing boards than we had design engineers back then. We had like 3 drawing boards. And I was one of the first to use 2D CAD. So trying to convince the engineering director that was a good path to take back in the kind of mid-90s. And yeah, it kind of grew from there, really.
In terms of time frame, just so we can get a little bit of scale on this, you mentioned before we started recording how long you'd been working for Alcon. You're a bit of a lifer, so what is that time frame?
Yeah, so I started November 95, so it will be 28 years later this year that I'll have worked at Alcon.
Okay, that's a respectable innings for sure. Now, I would have assumed that a company like Alcon, and I mean, obviously at this point, I don't know what they were advertising for in terms of a position. I would have expected sort of a prerequisite maybe of, let's say, a mechanical engineering degree or something similar. You know, you're going into an industry which is relatively complex and does require a certain skill set. So as you mentioned, that wasn't the case. You actually dropped out of a university degree to get into Alcon. So let's come back. What was that position specifically? I have no doubt it's changed over those 28 years a little bit.
It has, thankfully. So yeah, it was an apprentice design engineer. That was the role advertised, and that's what I started doing. And like I say, it was a small team of engineers back then. And so I had a very good engineering director who had kind of been in that kind of market area for a number of years prior, and so had learned an awful lot. And he had learned a lot from the person that had actually started the business, John Moore. So he was still the managing director when I started there, and he was kind of the managing director at AP Racing. He had moved on after that, but had kind of got this passion for race cars, having been a racer himself, for braking systems, had found himself in a market that wasn't really challenging for him. And that's how he came about setting up Alcon Components a few years prior. So yeah, we were in our 40th year as Alcon. So it was going 12 years before I started.
Right. So there's actually a tie-up here, AP and Alcon. You're saying basically the same manager or founder sort of worked in both companies.
Yeah, so I think AP Racing was part of AP Lockheed, and they kind of separated and created a racing division, and he ran that, and then he left and subsequently set up Alcon. So he came with, a lot of knowledge, and we've grown from that, really, from that little seed.
Interesting. I mean, obviously, two of the premier names when it comes to braking system componentry. Now, I'm interested in terms of your on-the-job learning. You mentioned some night courses here. So I can only imagine after dropping out of a university degree, jumping into Alcon, there's probably a pretty large learning curve that you needed to undergo. So what was that learning curve like? What new skills did you need to develop? And then what were these night courses? And was this something Alcon was supporting your learning as well? Or are you pretty much doing this off your own bat?
Yeah, as well as the kind of night courses, I was doing a day a week at college in order to be able to gain my HNC. So I didn't want to kind of give up on education. Obviously, that's invaluable when it comes to kind of learning as well as kind of on-the-job learning and application within an industry. So for me, it was kind of the best of both worlds. I was kind of learning the education side one day a week at college. I was then applying that during the rest of the week, but then also, learning from my colleagues and an application of, and, you sometimes learn from mistakes and you sometimes learn from others. And it was a fair mix of the both.
I'm interested with your sort of education and how you were doing this. You had this mix of on the job and then the night classes and a day a week. It can be difficult, I think, for a lot of people who are going through college or university, doing a degree or course or whatever it may be, but they haven't actually entered the workforce. So at that point, it's theoretical and they may not even have necessarily a firm application for what they're learning. In other words, they don't know how they're going to apply this knowledge or what field necessarily they're going to be working in. I kind of went through that as well with my own degree, and I found it a little hard sometimes. The concepts were a little difficult to really see how those were going to pan out in my future. Did you find that given you're already working in Alcon, you're seeing the application of your knowledge directly, that doing these night courses and the day a week was easier? You could sort of see that direct correlation with what you're learning to what you could apply in your job?
It definitely worked out like that. It certainly led for some interesting conversation with some of my lecturers about what they were teaching and how that differed to what I was kind of experiencing in the workforce. But, again, the lecturers were really open to those conversations. There was a number of people, the course was made up of people that were in a similar situation to me, but in very different industries. And so I think it helps to some degree to be able to share how, that worked really well. What you taught us last week, I've been able to kind of apply that, or if that's not the case, kind of explaining that as well. And they adapted the course, and I think it like I say, it worked really well for me because, you're applying some of the academic side, but also the application side, and you're earning a small wage as well.
Yeah, I think the relevance of that is there's the academic learning, and then there's the application of that and how that all pans out under a real world condition. And I mean, sadly, they don't always work out in unison there. So, I can only imagine that it'd been quite interesting, as you say, going back to your lecturers and saying, hey, that everything you taught me, that's actually doesn't really quite work out. So sorry about that.
Yeah.
Mate, hopefully that's not the norm anyway. All right, so another element with your time frame at Alcon, and you kind of just alluded to at the start, there were drawing boards, and obviously in 2023, I can't imagine anywhere outside of maybe Adrian Newey's office there's a drawing board. Now it's all going to be CAD, of course. So how did that, I can only imagine, given the timing you're talking about, you sort of lived through that transition from manual drafting through to CAD. How did that work out? Was there a resistance to adopt that technology? And obviously, it's an inevitable steamroller coming through. Once everyone got on board with that, how did that improve productivity and capability within Alcon?
Yeah, it's an interesting one. So, certainly when I started, I came with 2D kind of drawing skills. So I was more akin to drawing things in AutoCAD back then, whereas the engineering director at the time was very much hand draw. That's how he had kind of been brought up. And I think it was probably, looking back, a relatively quick transition when you start drawing things in AutoCAD and, he's doing things on the drawing board, and then you kind of need to do the left hand, and I do it in 5 minutes, and he starts a new piece of paper and starts drawing it all over again. It's like, I can see there's real benefit in this. So I think it demonstrated it for itself rather than, me really having to push it. He was slow to adopt it. He was very experienced in doing drawings, but he was quite happy for me and the other engineer to do all of ours in 2D on the computer. So, yeah.
I guess as time goes by as well, within a business like Alcon, particularly as it's growing, you sort of really want everyone to be on board, because one of the benefits, of course, of working in any of the CAD software packages is collaboration between different team members becomes much, much easier. We can get one team member working on one part of the design and someone else can be simultaneously working on another, and then they obviously can come together. Whereas I can only imagine doing that manually with a physical drawing, it's going to be a lot more difficult and time consuming. Now, let's sort of come back one step and let's just get a high level overview of the braking system. I mean, it sounds stupid because anyone listening has almost certainly used the brake pedal. And I think on face value, it's a pretty simple technology. It's a pretty simple system. But just so we're all on the same page, can we go through at a high level just what the braking system entails and how it actually functions in the car?
Yeah, no problem at all. So, you kind of mentioned there that the interaction that the driver has is with the brake pedal. So, you want to stop the vehicle, you press the pedal. So you're now converting a load in a linear kind of sweeping motion, and that's converted into a pressure through what we call kind of master cylinders. So they convert that push force by compressing brake fluid, and that generates pressure. So unlike air, which is compressible, brake fluid is almost completely uncompressible. So as you try to compress the brake fluid, then it moves within the system. And it's that pressurization and movement of brake fluid that travels through sometimes the actuation system, more often than not on race cars, directly through hoses and hard lines to the brake caliper. And then that converts that pressure into a movement of the pistons, which in turn press onto the back of the pads and clamp against the disc. And then it's that clamping with friction that converts the kinetic energy of the vehicle moving forward into heat. So all we're doing is converting energy in different ways in order to ultimately convert the kinetic energy of a vehicle moving into heat.
And this really becomes one of the key aspects with a race braking system or any performance braking system is this heat management. And what works for a road car definitely will give you problems when you take that same road car out on the racetrack and beat on it pretty hard lap after lap. So this is why we need to modify some of these components when we're looking at a performance brake system. So I guess on that note, where do you sort of see the key limitations with a factory production car style braking system when our interest is in performance and specifically maybe performance on the racetrack?
Yeah, so I guess ultimately, the standard road car package is manufactured for price constraints. So there's price constraints and there's application. You don't want to be designing new brake systems every time you do a new vehicle. So there's cross use of parts across vehicles, across platforms. And with that kind of comes some compromise. Yeah, a lot of it comes down to cost and part reusage, I think, that drive a lot of the limitations with the brake system. And it's built to, certainly road cars are built to a level of refinement that is always a bit of a compromise. So it works within a window, and that window tends to be more at the comfort end of the market rather than the performance end.
And I think another element, and we'll dive deeper into this particular point as we go through this conversation, is the design of a road car braking system. Obviously, everything needs to work effectively and really well from absolutely stone cold, or depending where you live in the world, maybe you're starting the car and it's minus 20 degrees C outside. And that braking system needs to operate from that absolute cold operating point, which comes down to a degree to the selection of the pad material. And conversely, we give away some of the performance at the higher end of the operating temperature, which is what we're likely to see on the racetrack. And again, we'll dive deeper into this, but conversely, a race car, if anyone's driven a race car around the pits with stone cold brakes, I mean, often it can be quite terrifying the first time you hit the brake pedal, because there can be almost no retardation until you actually build some temperature up. So, I mean, what works and is effective on a racetrack could be downright dangerous on the road. So it's very much chalk and cheese in terms of that regard, I believe. So if we're looking, I mean, Alcon as a brake component supplier, there's a range of sort of options depending on, sort of aftermarket or full-on race car application and sort of anything in between. So, I mean, it's a difficult question to answer, but can you give us some idea of the first components that need to be thrown in the bin and replaced when we take our production road car? And let's say we're a track day enthusiast, it's still maybe our daily driven road car, or maybe it's these weekend duty and the odd track day. So we want something that's going to kind of bridge the gap and work under both conditions. What would be your pick of the first things to replace?
I think the first thing that you kind of look at is probably the pad. The pad probably comes with the biggest level of kind of boundaries, i.e. it's designed to operate from cold, it's designed with a level of comfort. So changing that friction material is probably the single first thing that you could look at. Then kind of you go beyond that and you're into kind of the discs, the rotors themselves, and then you're into the bigger changes. So then you're into the physical size of everything. So the limitation of the size of the pad. So you look for a bigger sized pad, and with that comes a caliper to accommodate a bigger size pad. And generally, we always tend to try and get the discs as big as possible within the wheel. Bigger isn't always better. It needs to be, designed for the vehicle itself. But generally speaking, at the level we're at, where we're at kind of the ultra high performance side of the market, getting the biggest disc and caliper package that fits within the wheel is the kind of initial target. And that becomes one of the starting points for kind of design the system. We run the calculations, we look at pad sizing, pad areas, and then we kind of design the system almost predominantly around the pad and the maximum disc size that we can package.
Okay. You made a point there, which I think bears repeating, that bigger isn't always better. And I mean, I think as automotive enthusiasts, this is a trap that's super easy for all of us to fall into. And I've done this myself with just about any element of modifying a car. And that could be cam selection, turbocharger, or in this case, we're talking about brakes, obviously. I have also seen some tests on modified road cars where they've basically done some braking performance tests with a stock brake package and then gone to one of the generic off-the-shelf big brake kits where maybe the rotor's another inch or 2 inches, so 50 odd millimeters larger in diameter, as you say, just able to barely fit under the wheel that's fitted. and bigger caliper, bigger pad, everything that we think is going to add up to more performance. And I've actually seen a couple of these tests where the braking distance is either slightly worse or certainly no better than the factory braking package. So I'm just interested to dig into that comment you made that bigger isn't always better. Can you talk to us a little bit more about why that's the case? What are we missing here?
Yeah, so there's probably a few key things that you have to consider whenever you change anything on the brake system. And probably the first one of those is balance. A lot of people tend to kind of just look at the front brake sizing. And so if you make the front bigger, actually what you're doing is underutilizing the rear brakes. So you're asking the front to do more. Well, if the actuation system and the way the vehicle is set up is that it can't extract any more from the rear, all you're actually doing is losing efficiency at the rear brake. So balance is probably one of the biggest things that you have to look at whenever you're changing a brake package, is you want to be able to maximize the rear adhesion as much as the front. We always know that the brakes are bigger at the front. You get a bigger weight transfer for the front. The rear brakes are still doing a considerable amount of that braking to reduce those stopping distances. So that's probably one of the first key things.
Okay. A couple of elements just on that. So I just want to get in here as well that bigger braking package, if we just look at a single event stopping from, let's say, 150 kilometers an hour to stationary, that's not really, in my opinion, a really good and fair comparison of braking systems, because a lot of the elements that go into this bigger braking package is not just about that one-time stop. It's actually about heat dissipation and heat management, so you can do that same stop 5, 10, 20 times in a row, which the factory system almost certainly won't cope with. So that's a separate consideration that gets lost in some of these tests. So I just wanted to get that out there. Coming back to your comment about brake balance, and this is really easy to ignore, particularly if we're looking at aftermarket big brake kits for production road cars. Your point is quite common. We'll see front big brake kits and the rear is essentially completely ignored. So that kind of gets us into the situation that you're alluding to now. Before we talk a little bit more about that, in terms of the braking performance of the front versus the rear axle line of the car, and I mean, I get that it's probably difficult to give a rock solid answer here, but could you give us an idea, like a ballpark, what percentage of the braking is done from the front axle versus the rear? I mean, are we talking 3/4 of the braking is done by the front axle, or 2/3, or what's the line in the sand?
You're right. It's every vehicle is different. I mean, we do kind of front engines, mid-engine, rear engine vehicles. They have different kind of weight bias in their static condition. They have different aero packages. So dynamically, it's different. I would say if you were to average it all out, you're probably looking 65% front brake and probably 35% rear brake. But you're right. Every vehicle is different and will be a different number compared to that one.
The takeaway, even as a ballpark there though, 35%, if that's what the rear brakes are doing, I mean, that's not chicken feed. That's a significant amount, which kind of comes back to your point, getting that brake system balanced. Which then brings to the next question. Again, at this point, we're talking about modified road cars. This gets a lot easier with an all-out race car, because typically we'll have a pedal box and we can change master cylinder sizes, we can change brake bias. That's difficult or sometimes impossible with a street car. And I know I had this conversation many years ago. An ex-customer of mine ended up working for a government company here in New Zealand, which is basically in charge of making the rule set for modifying street cars, which we go through a certification process, basically presenting the car to an engineer and them ticking everything off and saying, hey, you've done this right, this car is still safe. And the conversation came about how they were going to deal with brake upgrades in the future, particularly with more modern cars where obviously we have ABS in pretty much anything that rolls off the showroom floor. I don't even know if non-ABS cars exist these days, but let's assume they don't. So we've got that element. We've also got electronic brake force distribution, stability control systems. And the point, which I haven't experienced it myself, but I get the concern, is that if we start modifying some fundamental components of that braking system, which is so pivotal to all of those elements I just talked about, surely the calibration of those systems is then out. And does that potentially make the car either less effective or potentially even dangerous? So I'm interested, what sort of Alcon's take on this? Is that a problem? Is it about matching components front to rear and testing, or is there a little bit more to it?
Yeah, so I mean, we have something similar in kind of Europe with the TUV approval, and it's something Alcon has kind of bought into, and we're able to kind of do TUV certification. Yeah, when it comes to sizing, you can't just suddenly go, and this normally comes down to kind of brake sizing and piston areas, especially kind of piston areas, that you have to stay within certain realms of the original factory equipment. You mentioned a few of those kind of, R-shy boosters, and a few others are some of the kind of systems that are out there that are appearing on vehicles. And they definitely become a limitation for the aftermarket. If you're not careful, you can kind of put the car almost into limp mode when it kind of comes to the braking system. So it is absolutely something that we're very conscious of whenever we're looking to do an aftermarket or a big brake upgrade, is what the actuation system of that vehicle is actually running. And we would only look to introduce systems that we would kind of be able to test and know that they actually work. So, we have lots of dynos, but we also have access to vehicles that we're putting these on, and we'll do real life kind of testing to make sure that we're not deviating from those kind of factory boundaries, if you like, for the actuation system. But you're absolutely right. It is something that we have to be mindful of, and probably increasingly so with new vehicles coming out.
I mean, from a layman's perspective, not having much involvement in braking systems at all, I would sort of think that one of the considerations here with, again, this upgrade path for a factory car would be sort of looking at the piston diameters of the front caliper in factory form and the relationship of that front piston diameter to the rear piston diameter, and then maybe trying to retain a similar split front to rear with an aftermarket caliper, albeit probably bigger, maybe with more pistons. Am I on the money there, or is it much more complex than just that?
It is getting more complicated than that. So certainly, with standard booster type systems, so servo boosters and things like that, to maintain the balance, then yes, we'd be looking at front piston area and rear piston area and the balance. We would be doing our own calculations because, as we alluded to earlier, there are kind of compromises that the factory make with part availability. So they don't always get the balance exactly where it should be. And so there is, additional benefits that we can reap from having a system that's designed specifically for that vehicle. But generally, we would always need to look at both front and rear sizing and kind of size up accordingly. With booster systems, then where it's getting more complicated is the systems are able to measure and respond to volume increase. So the amount of fluid that is absorbed into a system as the brake caliper kind of expands and applies that clamp load. And so even if you matched the same piston area, but you had a different characteristic, so with different running clearances, different volume consumptions, then the system can struggle to kind of understand what's going on. And it actually thinks that it's in like a brake fade scenario, and it can react accordingly. So it almost goes into an emergency brake case thinking that something peculiar is going on with the system, whereas actually you've just changed something outside of the boundaries for which the code was written.
Sounds like essentially the braking system in modern automotive applications is presenting the same sort of issues for the likes of you guys at Alcon as the same technologies that are being applied to the modern crop of engine management systems, making our life more difficult to modify the calibration. So probably no surprise, technology marches on, everything gets smarter. Sometimes from our perspective though, not necessarily for the better. All right, let's move into some of the components that we would consider for a race application. I sort of want to go through the braking system and talk about the relevance and sort of why we choose certain parts. So for a road car, we're going to have you mentioned the term booster before. So a brake booster, which is vacuum driven, it uses the vacuum from the engine to help assist the driver when they put their foot on the brake. So essentially, in a nutshell, it means that we don't need to apply so much effort to the brake pedal in order to get retardation. Nice sensitive brake pedal. Sounds like a great thing, and I guess in most applications it works pretty well. Typically we see for a full-blown race car the brake booster is thrown away and instead a pedal box is used, and as its name sort of would suggest, it is a box with 3 pedals on it. You've got your clutch, you've got your brake pedal, and generally the accelerator will be attached there. I mean, really the key for this, we're only interested in the brake pedal, and one of the elements that comes along with this is not only getting rid of that brake booster, but the ability to have an individual master cylinder for the front and the rear brake circuits. So break that down for us. Pun actually not intended there. Why would we get rid of that brake booster? What is the benefits of doing so? Because anyone who's driven a race car with a pedal box would know that the brake pressure, the exertion required to get the car to stop is incredibly high compared to a road car.
Yeah, so I guess there's probably a few reasons why. Weight is probably one of them. So the brake boosters aren't small. They do tend to be quite large items. So packaging them within a race car can be problematic, but also you're carrying that weight. And we're ignoring kind of regulations because obviously there are some regulations that prevent the use of kind of aids like that. So if you had the choice, yeah, weight is definitely one of them. I think the one of the other reasons as well is you kind of lose some of that interaction with the brakes. So it's a bit like when we went from kind of, to electronic steering kind of and things. And people sometimes say that the steering just feels a bit disconnected from the wheels and you don't get that feedback. With a system that doesn't have boosters, where you're applying your foot on the pedal and generating that pressure that goes to the brake calipers, you get more feedback. So when you're on the limit of adhesion and you're trying to prevent lockups, but you want to be at the maximum point of adhesion, I'd always argue that a system that has a kind of pedal box and, Alcon calipers is more kind of, giving you that feedback, and you're able to interact and feel what's going on at the brakes an awful lot more.
Yeah, I mean, I think it's the ability for the driver to get that feel that you've just mentioned. I'd also say consistency is a big factor. And I mean, it's difficult because, not every factory brake booster or brake assisted braking system operates the same. Some are great, some are absolute rubbish. I have my own data point, which is our Toyota GT86 race car, which currently still runs the factory ABS and the factory brake booster. And the problem I see with this on our local track is, it'll be perfect and consistent for 4 laps, and then on the 5th lap in one particular braking area, which is a high-speed braking area into a hairpin, the feel of the pedal completely changes. And that is a horrible feeling for a race driver. The thing you want is to know that every time you touch that brake pedal, it's going to feel the same and it's going to respond the same, because if there is that inconsistency, it puts doubt into the driver. And when you're driving around with that sort of little feeling in the back of your mind, it makes it very hard for you to be able to concentrate and drive the car 10/10ths consistently. So I think consistency of feel and modulation of the brake pedal probably would be the 2 key elements that I would pick out there. The other element that sort of comes into this is the dual master cylinders. And we've sort of already alluded to this here in terms of brake bias, which we don't get the ability to change in a factory braking system. So can you talk to us about brake bias, what it is, why it's important, why we may want to adjust it, and how that's actually done? So a bunch of things there. Let's dive into those.
Yeah, I mean, just on your previous point as well, probably one of the best comments that we can ever receive from a race driver is that he has total confidence in the brakes. And that comes down to exactly what you were saying about consistency. It's just doing the same thing. If he has confidence in the brakes, he will be a faster driver as a result. So that's kind of one of the best comments we can ever get from asking how the brakes are with the race driver. He kind of comes and says, yep, no worries, total confidence. And you just know that you've kind of, yeah.
I mean, I think on that note, it's easy, and that's why we started with this conversation. It's really easy from a layman's perspective to think the braking system is pretty straightforward, right? It's a brake pedal, it's some calipers and rotors and some brake pads. I mean, how complex could this be? But when you actually start getting down in the weeds with it, it's actually a hugely complex system with a lot of interactions that aren't on the surface maybe immediately obvious, and all of these interactions and the design of the system can have less than subtle effects on the performance of the car and that feel and confidence that the driver has. Right, so let's get into brake bias anyway. What can you tell us about brake bias, Steve?
Yeah, so exactly what you were saying. When we run our pedal boxes, we run dual cylinders. One cylinder is dedicated to the front axle and one cylinder is dedicated to the rear. So when we're talking about brake bias, or brake balance. We're talking front to rear brake balance. So being able to run dual cylinders gives you a level of tunability between the front and the rear. So without having to change calipers with the piston area. So, we've got a setup and we want kind of more brake bias to the front, then we can make some reasonably substantial changes to that by changing a master cylinder diameter. We're still in the old kind of imperial world with master cylinders. So we start at kind of 5/8 and we kind of go anything up to like an inch, and it's every kind of imperial size in between that. So that gives you a pretty significant change, either by going up or down in size and having total kind of freedom to change fronts independent to rears. And then we have a fine tune that we do with a balance bar. And a balance bar is almost as the name suggests, the master cylinders are connected to the end. So it's like a beam. And a 50/50 is you press exactly in the middle. And the force that you press in the middle, you're distributing that force evenly to both master cylinders. And then when we change the bias, we're basically changing the pivot point at which we apply that. So usually on a screw thread, and you wind it to either front or to rear. And all you're doing by doing that is changing the point at which the brake pedal is applying the load relative to the midpoint. So, you move it closer to the front, you apply more load, you get more pressure, you get more braking force at the front. And then that works both ways. So you have a certain degree of tunability on the bias bar. But if you run out of tunability, that's when you're into a master cylinder change. You try and bring it back to the middle again, and then that gives you the tunability.
Okay, yep. Now, this is yet another one of these conversations on the podcast, which is super easy to understand when you've got the benefit of a picture. And what we'll try and do is I'll chuck our producer under the bus here and task him with finding a nice simple drawing that we can chuck in the show notes there, just to simplify that for people who aren't maybe picking up what we're putting down. But it is, on face value, a relatively simple system. Just to paraphrase what you're saying here, essentially you've got the course adjustment, which is your master cylinder size relationship front to rear for the front circuit and the rear circuit, and then your fine adjustment is the balance bar. In terms of that, if you're sort of maybe a little bit out of the ballpark maybe on your master cylinder sizing, and you're really kind of wound all the way to one extreme of the balance bar to get your braking matched, is there any downsides on that, like operating permanently at or close to one extreme of the brake balance bar travel? Or will we get better consistency and repeatability if we size the master cylinders so that we're operating at or very close to the sort of midpoint of that balance bar under normal conditions?
I would always prefer that we're kind of operating it as close to midpoint as possible. You do lose a small amount of efficiency in the balance bar setup as you go to the extremes of adjustment. But the one kind of, I won't say problem, but the most kind of common misconception with balance bars is that you want everything set up parallel with no kind of application of the brake pedal. And how you should have it is with kind of a typically hard stop. That's when you want kind of the balance bar to be perpendicular to the pedal. So as you adjust it, actually what you should be doing is winding the push rods in and out to adjust that start position. So when you start to get to the extremes, what you tend to find is that no longer are you operating with the pedal kind of perpendicular with the maximum brake apply. If you can be more towards the center and just be able to tune a few percent either way, then the system will work better for you.
I mean, the other element, which kind of goes a little bit beyond our conversation, but worth just touching on, is the brake bias is a really important adjustment for the driver in terms of being able to adjust the balance and braking performance of the car during a stint. And that might be as the track evolves, maybe as the fuel load burns off, particularly for an endurance car that might be starting out with 100 litres of fuel. As that burns down to next to nothing, that's obviously going to have an effect on the balance of the chassis, which in turn can affect the ideal brake balance. So that's an important adjustment. I'm going to also assume that if we're sort of starting with that brake balance bar kind of close to 50-50, obviously that gives the driver more flexibility in terms of moving that balance towards the front or the rear. If we're kind of already at the extremes under a normal condition, obviously that limits how much travel. Another obvious reason for changing that balance would be weather. A dry balance, we're going to probably have more front bias than a wet balance where we don't get the longitudinal weight transfer under braking, so we can actually utilize more rear brake. So that's an element I wanted to just sort of touch on there. The obvious question that comes up from this, which again, I'm going to just assume that it's not a nice, easy black and white answer, but people are obviously going to be asking, okay, cool, this is all great, and I understand what you're saying here. How do I choose the correct master cylinder size for my application? So is there any guidance you can give, or even if you could point to another resource where you can go through a design sheet and sort of calculate that?
I mean, we have our own internal kind of calculations for doing that. So the more information you know about your vehicle, so center of gravity, the height of center of gravity, weight distribution in its kind of static case, wheelbase, and all of those sorts of things get kind of put into our kind of calculations. Obviously, if we've designed the braking system, we know what the disc sizing is, what the effective radius is, what the piston area is for the calipers. And that gives us a very good starting point for where we would recommend starting with master cylinders. So generally, we're giving some advice to race teams as a good place to start. I know if you're kind of a day racer, you probably don't have access to quite so much of that. But yeah, I've only ever used Alcon's calculations for kind of doing that. But I would always say, if you have a setup that's worked and then you're changing the brakes, always look at percentages. So how much you're increasing the front, how much you're increasing the rear. And if you can keep the percentage ratio change same, you're probably not a bad start point to go from there.
It'll get you in the ballpark if nothing else.
Yeah.
Okay. In terms of actually validating the brake balance or bias, we're using pressure sensors in the front and the rear circuit to calculate that?
We can be. I mean, that's normally the way that the race teams will get the kind of feedback. So we're getting live data, looking at kind of in-stop kind of brake balance, in-stop pressures. We're also looking at whether we're kind of locking wheels and what that kind of transfer is. So certainly when we're kind of working with race teams, they're collating a huge amount of data that their system engineers kind of really understand as well. And then, they'll share some of that. And if there's something that doesn't quite sit right, or they're not quite able to feel like they're getting the max amount of the system, then that's normally where we kind of get involved, and we'll kind of give some advice as well, and for things to try to overcome that.
In terms of that brake balance as well, not to sort of go on about this topic, but I think it is quite interesting, so it's worth diving into it a little bit further. I can assume here that with a well-designed pedal box, and if everything's working well, you should be able to maintain a reasonably consistent balance or brake bias front to rear as you press harder and harder on the pedal. And at least as far as I'm aware, I think that's one of the things that the design of a pedal box is kind of focused on, making sure that it's consistent in one brake application after another and remains consistent as the brake pedal is pushed harder. Is that what the car wants, or is this just a compromise because it's a mechanical system? And what I mean by that is I could imagine that under a very, very heavy brake application, maybe a high speed into a hairpin, where we're absolutely at the maximum adhesion of the tyres, we're going to have maximum longitudinal weight transfer, less grip available from the rear tyres compared to the front, so that would in turn require a more forward bias to prevent rear locking, versus there'll be situations where we come into a braking zone, but maybe it's not actually a hard braking zone, and it's more sort of we're just brushing the brake pedal to scrub a little bit of speed and maybe a slight weight transfer forward to get the car to turn in sharply or cleanly. Under those conditions, because we've reduced that weight transfer longitudinally, I could imagine we could utilize more rear braking. Is this a consideration, or am I completely lost here?
No, you're absolutely right. I mean, brake balance is usually done for where you're doing full hard stops. So what you don't really want is the rear brakes locking before the front, because it gives the vehicle instability. So the brake balance is kind of designed such that the fronts would always lock before the rears. And so for every other stop, you're right, you're not actually operating within the kind of idealistic brake balance, but then arguably, does it matter?
You're not actually asking for maximum retardation in those other situations anyway. So if you're not maximizing the rear, is it an issue? That's what you're saying?
Exactly, yeah. But interestingly, brake bias does change during a stop itself. Obviously, when you first hit the brakes, the aero front to rear, weight transfer, and all of those sorts of things are dynamically changing. So I certainly know from experience that we're involved kind of in looking at dynamic systems. You have to be careful with what regulations you're kind of operating under. But in an ideal world, you would have a brake system that dynamically changes. And we'd looked at all sorts of ways. And this isn't only front to rear. This is kind of when you're braking and you're turning in and you're getting a left to right balance as well. And so we were looking at systems for kind of ultra high end kind of race cars where they were looking at kind of suspension travel and whether they could adopt and use that to be able to have a kind of a 4-point kind of brake bias. So it distributes weight front to rear, left to right in order to be able to maximize the brake balance based upon the tire adhesion and the weight transfer and everything. But regulations are normally the limitation with developing systems any further than that.
I think that is an interesting point you raised, because on face value, unusual wear patterns on our race car left to right. And most people sort of consider the balance front to rear, but this left to right situation that you just mentioned is interesting, and I'd never experienced this. We have one particular racetrack on our endurance calendar where we have a really high speed straight, and at the end of that straight, we've got this sort of awkward kink left into the braking zone. So you're sort of, depending on the speed of the car, you're either sort of braking just before this kink, then sort of getting off it, turning in, and then braking again, or maybe you're just past the kink before you're braking. Anyway, long story short, you're sort of kind of at the end of that braking zone, mixing, turning, and braking. And with a conventional mechanical brake system, you're going to obviously risk there maybe potentially locking, it's a left-hand corner, so potentially locking the inside left as you unweight that. Our car still runs a factory ABS system, so it's all over that. So as far as the driver's concerned, you can almost treat the brake pedal like a switch. The problem we were seeing is after a test day and a quali session, the front right brake pad and rotor were almost worn out, and the front left was maybe 50% worn. And that's simply because you're turning left, so you're loading that front right much more hard than the left. So the ABS system can apply more pressure. There's more braking force available. So basically, it's working that front right corner of the car harder than the left. And that's the only track I've seen that in. It was a really sort of a bit of an eye opener for us, but obviously still just requires management, as with any other element of the braking system.
Yeah. A bit of an interesting one for you, Andre. It's a bit of a far right kind of comment, but we designed a brake system for a NASCAR where they go on the ovals and they're kind of running always in the same direction, usually anti-clockwise. And they ran a different brake package on the left to the right of the car. So they ran different piston areas on the left-hand side to the right-hand side on the rear, so that when you hit the brakes, it helped with turning. So yeah, it's interesting what dynamics you can actually achieve with the brakes.
Obviously, that is a very niche application, but an application nonetheless.
Yeah, I wouldn't recommend it for anybody else, but yeah.
No, yeah. Probably not. Let's move into the next part of the braking system I want to talk about. I think we've done our pedal box now. Let's talk about brake calipers. And again, we sort of talked about the case that maybe bigger isn't always better, but typically we're going to see when we move from a production style brake system to something aftermarket, we're probably going to end up at least at the front of the car, maybe with a 4-piston caliper, maybe a 6-piston caliper. What was the consideration there? Why do we want to add a bigger brake caliper? Why do we need more pistons than the factory caliper that came off?
So probably the first thing that we will change compared to factory is that we run opposed piston calipers. So we have pistons on the inboard side and the outboard side, and it's either a 2-piece or a monoblock caliper, as opposed to, we know them as pin sliders. So it has just an inboard kind of piston, and as it pushes one pad, it pulls the cradle and pulls the other pad.
I'm going to actually hope that anyone listening to this with a performance car is not still running a slider style caliper. I do know exactly what you're talking about. We do still see those slider style calipers used sometimes on the rear of sort of would we call it a semi-performance car? But hopefully the braking system already has opposed calipers. But if not, that's an obvious upgrade. I've seen no end of problems with those slider calipers, particularly on older cars where the slider mechanism tends to rust up and freeze, and all of a sudden you're wearing out one side of the pad and the other one's basically hanging out, being cool and doing nothing, correct?
Yes. Yeah, no, exactly that. Yeah. So in answer to your question, kind of as far as piston kind of sizing and quantity is concerned, a lot of that comes down to the pad selection. So we will choose a pad based upon the achieving the surface area to give us the correct work rate of that pad. And once we've selected that pad, we're looking to maximize the pressure distribution, even pressure distribution across that pad. Some pads are kind of, relatively long and have a narrow annulus. And so actually having a 6-piston caliper where the pistons are on an arc matched to those pads would give you a better pressure distribution than having 2 larger diameter pistons. The ends of the pads wouldn't see the same pressure, and so you lose in efficiency through that. So a lot of the kind of the layout of the pistons, the sizing, comes down to the pad that we're actually running in that caliper.
It sounds like the first consideration is the pad, and then that drives the caliper choice based on getting this pressure distribution correct. And I'm guessing what you're saying there, for a longer pad, if you went to a 2-piston opposed caliper, you've only got 1 piston per side, and if that's pressing directly in the center of that pad, essentially it's going to bow out, and each end of the pad is essentially going to have no pressure applied, so it's going to do no work. Is that kind of a rough summary of the situation?
Yeah, that's an extreme example of what we're kind of talking about. So we'll run FEA analysis on our pads and the pistons, looking at that pressure distribution, and we can look at reaction loads throughout that pad and see if we've kind of got the right distribution of loads. We spoke earlier that we've kind of, at this point, we've already probably selected the total piston area that we want to achieve based upon the brake sizing and the vehicle dynamics. So now it's about, okay, how do we divide that total piston area by the right number of pistons and the right diameter of pistons?
Yeah. Another element that we see with higher end performance calipers is that the piston size is often not the same. I believe the term's differential piston size or piston bore. And can you give us a bit of an understanding of why that's done and what the benefits are of that differential sizing?
So differential piston sizing is all about counteracting pad taper, and this is end-to-end pad taper. So what you tend to have is on the leading edge of the pad, so the edge of the pad that kind of runs to the rotating first part of the disc will bite into the disc. You also get a small amount of kind of pad kind of transfer as it kind of along the pad. And so whenever you look at differential pistons, you will always see that leading piston is smaller than the trailing end. And it's counteracting the fact that as the pad bites in and you get that transfer, you need less pressure on that end of the pad. And so we put a bigger piston running at the same pressure gives more clamp load. So it counteracts that, and you end up with as flat a pad as possible throughout its whole wear life.
You're essentially trying to optimize the pad wear, keep it even, and then optimize, therefore, the pad life.
Optimize the pad life, but also with pad taper, when it gets particularly extreme, drives for inefficiencies within the brake caliper and ball wear within the caliper as well. So the pistons will always try to align themselves with the pad, and so they'll tip in the piston, and you can kind of get rubbing of the piston within the bore of the caliper, which is inefficient. On kind of road cars, it can lead to a noise. You want as flat a pad as possible, flat contact in the disc, but also flat throughout its thickness as much as possible.
Yeah, that makes perfect sense. Talking about the construction of the caliper itself, you just mentioned previously a 2-piece versus monoblock. So this comes down to the construction design considerations. What are the pros and cons of those two techniques? Are there other techniques, and what drives your decision?
So those are the two main options that we have available within our portfolio. 2-piece gives you some flexibility on disc thickness, so you can make minor changes to the machining and be able to accommodate different pad thicknesses or different disc thicknesses, without a substantial change to the design of the caliper itself. So where we're doing applications that maybe run a range of disc thicknesses, then two-piece kind of lends itself to being able to be more adaptable for that scenario. Probably the downside is that generally like for like, it's heavier, and also you will struggle to get a caliper to be as optimized and as weight versus stiffness efficient as what a monoblock could be. All of the monoblocks are kind of machined as a much more optimized, not having to worry about kind of bolts and the material that they need around them. The high-end race calipers would always tend to be monoblock just because it gives you more design freedom when it comes to optimizing, reducing weight, maximizing stiffness.
Sure. Now, there's a couple of elements that I want to dive into on that topic. So I'm picking up here that probably makes sense that the monoblock design is going to be almost certainly a more expensive caliper to manufacture compared to a two-piece. In terms of the sort of balance between weight and stiffness, obviously anything that's sort of related to a race car, we want to be particularly careful about weight, but an element of the braking package is that's considered unsprung weight, which has quite a big knock-on effect to the performance of the suspension system and how the car's able to negotiate sort of irregularities on the racetrack. Probably the bigger consideration here, which we'll get into, is also the weight of the rotor. Probably, usually the rotor is going to be a more significant element of that unsprung weight than the caliper. But getting into the stiffness, why is the stiffness of the caliper so important to the design of that entire system?
Okay, so it goes right back to probably one of the first things that we talked about, and that was the kind of pedal feel. So what the driver feels when he pushes his foot on the pedal. When we kind of were talking about we're displacing fluid and we're pushing that fluid to the calipers themselves, as the caliper bends, and if you imagine it's almost like a giant G-clamp, as that bends, then it requires fluid to enter the brake caliper in order to be able to maintain that pressure within the system. And that fluid comes from the master cylinder, and the more fluid that you have to push into the brake calipers, the more pedal travel that you will feel. And from a race driver's point of view, they're always looking for not only a consistent pedal, but also a short, stiff pedal. They don't like long, kind of soft pedals. They like something that is firm, where they can feel the bite. And so we're always trying to maximize the stiffness, minimize the amount that the caliper opens and the compliance of that caliper, and therefore the volume consumption, as we call it, within the caliper for a given pressure.
Yep. Again, this really sort of comes back to just driver confidence, and there is nothing worse than a long pedal. And I'll talk about another element that can result in that shortly, but the stiffer that caliper, obviously, the less flex, the better the pedal feel is going to be and the more consistency. In terms of this, I can only imagine that the advent of 3D modelling and FEA specifically, which you already alluded to, has been a really big driver in being able to go through iterative designs of the caliper in terms of optimizing the weight stiffness relationship.
Yeah, massively. So, I mean, if we go back to when I was kind of doing Formula One caliper designs in kind of the 2005, the way that we used to do it back then was quite an iterative process. So we would kind of design a caliper, we would analyze it, would kind of do all the FEA for stress and stiffness, and we would look at areas that were underutilized and inefficient. We'd take material out, we'd add a bit of material in, we'd rerun it, and we'd probably do that 30 or 40 times as a kind of iterative kind of change process over a period of a few weeks. But jump forward a few years and we introduced topology optimization software into Alcon. And this is a fresh approach to kind of how we design calipers. So something we've been using for many years now, but it kind of works almost the reverse. You design a very, very basic caliper that has the pistons in the right place, fits within the package space that you have within the wheel and the upright. It has the right kind of disc pathway for the disc and everything, but it's a very rudimentary, it's a very blocky caliper. We then put that into the optimization software. We apply the pressures, we apply the dynamic loading case, and that mathematically goes away and calculates, in theory, the most optimum shape for a given set of target values for deflection. And we then take that optimization run and we rebuild it into CAD. taking into account DFM and the manufacturing route that we're going to take, which is almost certainly always 5-axis machining from billet for a lot of the motorsport applications. We reproduce that, and that's the shape we get. So for the given criteria that we entered into the system, it's mathematically the best outcome that we could come up with.
It's sounding very much to me like generative design, where you can use a 3D modeling package to basically design something, give it criteria. Maybe you're solving for minimum weight, maybe you're solving for the ability to withstand a certain loading or a combination of those parts. And then you kind of let AI take over the reins and you come back to a design that's been optimized for your criteria. What I do see typically with generative design, and we've talked about this on the podcast previously, is you typically get a very organic looking product design, which often may not lend itself well to traditional manufacturing techniques. Quite often there actually would be impossible to manufacture without the likes of 3D printing or the like. So certainly, some of those designs you couldn't manufacture using a 5-axis CNC. Is that sort of, am I picking up that right? Is this sort of topology optimization similar to AI, but more with a drive towards coming up with a finished result that can be cost effectively and easily machined?
Yeah, so I think this is really where the experience of the design engineers that are running the software, we're always looking for a design that kind of converges, i.e. it meets the criteria as best it can for weight and for stiffness and for stress and all of the other elements that we've kind of put into it. We end up with a very kind of element-based kind of output from that. And that's really then when the skill of the design engineer who's rebuilding that into the CAD system is having to look at the functionality aspects. Is it going to be internally drilled? Are we going to have an external pipe? We need access for the bleed screws. We need to be able to make it. And they're rebuilding it with all of those things in mind. And so, if we're rebuilding for a 5-axis manufacturing route, then they're looking for tool access and radii and all of those sorts of things in order to be able to come up with a shape that actually meets that brief. We have designed calipers for 3D printing. They're not kind of constraint free. It's just a different set of constraints that you have to consider when you're designing for that. But it is coming along. It is moving on. It's just still at a price point that is possibly still out of reach for most. And there are still concerns around the kind of repeatability of such a process for a safety critical part.
We'd like to definitely not see the caliper fall to pieces. That'd be sort of a given assumption. Talking about the actual manufacturing, you've already mentioned these monoblock race calipers are typically CNC machined. Obviously, when we look at the design, the manufacturing options, CNC machining, a lot of flexibility, beautiful parts that are produced, but the downside is, I'd say, probably a little bit more cost involved and time consuming than if you were to go down the path of maybe a casting manufacturing process. What's the driver here? Are there too many advantages to the CNC machining that sort of offsets its additional cost from going down the path of casting, or is the casting too limiting in terms of what you can do with that caliper in terms of making multiple designs? Again, I don't get involved in this myself, but I understand sort of casting would be a more traditional approach to a high volume part manufacturing versus CNC machining maybe being more suited to small production runs.
Yeah, no, I mean, that's exactly it. The restriction with castings is the investment up front. So the tooling cost investment is quite significant. And so if you're designing for a motorsport, the volumes are going to be relatively low and designs change year on year. So they're forever evolving, forever changing. They've got different kind of, maybe this year they're more concentrating on weight. Maybe, the following year, actually, they want a stiffer system. Maybe they've changed the wheels. Maybe the regulations have changed. The designs are always evolving. So nothing stays stationary long enough to justify the investment in the casting. So for almost all motorsport applications, and there are some exceptions, things are machined from billet because it gives you design freedom. It suits the low volume. You're not really making any investment in tooling. So yes, it generates a higher piece price, but you're not spending, tens, if not hundreds of thousands on casting tooling. And arguably, you touched on it there. You make the investment in casting in order to be able to get a quicker machine time, a quicker throughput of components. So it may be that you're up against it with cost, and you need to have a lower piece price cost. It may also be throughput of parts. If it's taking you 9 or 10 hours to machine a part from billet, you wouldn't want to do thousands during that route. Otherwise, you'd have banks of machines just churning these things out. So it very much is kind of the right product for the right application.
Yeah. I think it's also worth mentioning here that even if you're casting a part, it doesn't sort of come out ready to rock. Like there is still finished machining operations. I can, again, not being involved in this personally, I mean, I can imagine you're still going to have to finish the piston bores and a bunch of other machining operations. So it's not sort of a one and done operation. There's a bit more that goes into it. I do want to move on though, because I've got probably about another 3 hours of questions here, and I don't want to run out of time. I just wanted to take a moment out of our interview with Steve to talk about a course that I think you're really going to enjoy if you are enjoying this chat about braking systems, and that is our Race Driving Fundamentals course. This is going to be perfect for anyone thinking about maybe attending your very first track day, through to those people who are regularly competing in a race series and want to improve their skills and drop their lap times. This course is ideal regardless what camp you personally fall into. We'll start by talking about vehicle dynamics, aspects such as the traction circle and what's actually happening as we transition from braking to cornering and then to accelerating. This also plays into weight transfer in the car. We'll talk about handling balance, understeer and oversteer, and how we can manipulate the general handling balance of your car. A lot of this comes down to the application of braking, and specifically trail braking. We'll also talk about heel and toe, ABS versus conventional braking systems, and brake bias. We then dive into the cornering phases. We break the corner down into different phases and teach you how to deal with each of those individual phases. We also talk about driving lines. Really, really critical here, understanding the driving line and how the driving line you choose is going to influence your pace through a particular corner or section of track. This really comes down to prioritizing certain corners on the track as well. We'll also talk about different ways you can improve your driving, such as onboard video, visualization, track walks, simulators, and data analysis. If you are interested in purchasing this course, we will give you the coupon code ALCON50, that's ALCON 50. That will give you 50% off the purchase of that course, and again, we'll put links in the show notes to make it super easy. Let's get back to our interview now. One of the elements, and again, this comes down to maybe breaking down some of the misconceptions. We talked about pad size, and there's another element with the pad. The compound sort of dictates the way the pad will work in terms of its friction coefficient, also its working temperature range, which we've also already mentioned, kind of the ideal range for a road car, quite different to a race car. I think most people would expect that a bigger pad gives more friction or more sort of retardation to the rotor. Is that actually the case?
It's not actually the case, no. So a bigger pad will give you more heat capacity. So it's about repeated stops. It's about the number of stops you can do before you exceed the heat capacity of the brake pad and the brake system. So for just a one-stop application, you wouldn't generally see much difference between kind of a large pad and a small pad. If the small pad has been sized for one application, then that's fine. It's about repeated. So if you're going on a track and you're doing multiple laps, you're doing those multiple brake applies, and it's the amount of heat loss that you get between those brake applies that means that you need a system that's sized accordingly that can actually cope with those repeated stops.
Yeah. Let's talk, while we're on the topic of pads, let's talk a little bit about the compounds that are available. So I kind of already alluded to the fact we've got different friction coefficients and different operating ranges. So what do we need to know when we're sizing this? I mean, choosing, I should say. I could imagine that the operating temperature is kind of going to be driven to a degree by what is generated on the track, which is going to be a factor of the available cooling airflow, maybe the size and weight of the car, and essentially how fast you're going, how much retardation is required. So that's probably kind of a given in terms of what is needed. With those friction coefficients though, does this come down to choosing a pad that suits the particular driver's request in terms of something that's nice and linear, or something that feels really grabby, that first hit of the brake pedal? How does it affect the feel of modulation with a non-ABS system, be able to modulate that right on the point of lock up? And what do we need to know?
Yeah. So, I mean, when it comes to pad selection, it's a massive kind of market out there. But you're right. There's the ultimate friction. So the amount of mu that you get at peak. You also get kind of hot performance temperature, cold temperature performance, initial bite. I think you alluded to it then. Some people like a pad that kind of grabs and then it kind of drops off a little bit. Some people like a pad that kind of ramps up, so it's not too grabby initially, but then they start to feel the friction kind of ramp up as the temperature ramps, and like kind of pretty flat line. Cost is obviously a consideration. Pad wear, different pads wear different kind of ways. So it's really hard to say that, a particular pad is right for a particular application or a particular circuit. There's plenty of examples where they don't even run the same pad friction front and rear because they want different characteristics on the front axle to the rear axle. What we were talking about with kind of the balance and the fact that the balance changes during a stop. One of the ways to maximize the fact that we've got a kind of a constant balance is to have a pad front and rear that change during that brake event. So, if you've got more bias towards the front, having a pad at the rear that starts with a higher friction, but then kind of falls off, maybe one of those ways of actually getting more efficient use of a rear brake package whilst maintaining a more forward biased system. So yeah, it's a whole world of choice out there for everybody.
A couple of elements that you just raised that I think are worth just maybe sharing a little bit of my own experience. So we've got two race cars currently. We've got the GT86, which I've kind of already mentioned, big brake package front and rear on that. And I think probably ultimately when we look at the brake temperatures, I've got the benefit of infrared brake temperature sensors on all four corners on that car. So we really can monitor what's going on. And essentially the rear package is probably oversized for the car. So one of the changes we made last season was actually to go to a more aggressive rear pad to, as you were talking about earlier, trying to maximize the braking performance of the rear axle, which for the most part had previously just been along for the ride. We did see improvements in the stopping distances of that and the consistency. The polar opposite of that, we've got another race car which couldn't be more different. It's an EF Honda CRX fitted with a built K20. The whole car weighs about 800 kgs, 850 kgs, and it's got a very front heavy weight bias. And with that car, the rear brake package is kind of along for the ride, and you do need to be a little bit careful with it because if the rear is doing too much, you do risk having problems with the rear locking. I didn't build that car, I'll probably point out, and the guy that we purchased it off had gone through quite a lot of iterations. He'd actually ended up with a Willwood braking package on the rear, and that actually ended up running a pad that's designed for an aluminium rotor, of all things. And the supplier said to him, hey, look, this isn't suited to what you're doing, but he'd gone through all these iterations of different pads, and that was the only pad he could get which wasn't aggressive and caused rear locking. So yeah, just a point there to kind of back up what you're saying. There's not a lot of black and white essentially in anything we've been talking about today, but there's not a lot of black and white in choosing your pad compound, and there's some considerations that need to be made. Leads to the next question. Pads can be expensive. We don't want to be going and testing sort of 10 different compounds in our race car to try and find the one that suits our magic criteria. Have you got any advice that you can give to our listeners when it comes to getting their own advice, I guess, on which way to go with brake pads and where to get started, so they're hopefully at least in the ballpark and aren't going to be wasting thousands of dollars going through set after set of brake pads?
So I suppose, generally the pad manufacturers should have data sheets for their pads. I think it's one of those things, if you know what you're looking for and you can understand how to read the data sheets where they kind of give the friction curves, and you can kind of look and say, well, actually, yeah, I don't want something that comes in that's too kind of initial bite to kind of high friction on the rear, then actually looking at those manufacturers' friction curves is a really good place to kind of start. You kind of mentioned cost. We have kind of dynos, 2 dynos in our facility, and it's they have been used in order to kind of create pad matrix. So race teams will come in with tens of different pads, and they'll run a generic sequence on the dyno in order to be able to generate that information, so that when they sit down and kind of are making those choices, they're making it with data that they've collated themselves. It's completely independent in order to be able to make those decisions. But yeah, if you don't have access to that, I think the better kind of manufacturers out there should have data sheets. If you can find them, great. If you can ask for them, even better. And it's just about being able to read what they are actually telling you. So, where we're talking about, something that's high friction and quite linear, then you're looking for something that is sitting at those kind of 0.4, 0.45 mu kind of consistence. 0.4, 0.45, I'd say is a pretty good mu. So anything less than that is the lower mu level. Anything higher, that starts to become kind of what we would consider high mu pads.
Okay, well, that's a good sort of rule of thumb to have in mind. The other thing I'll add to this conversation as well, because most people probably aren't going to have access to a brake dyno, and at least initially, other than the information you just given, maybe even reading the manufacturer's data sheet for a brake pad might not be sort of that useful when you're just getting started out. But irrespective of where you are in the world, there's going to be race brake suppliers, and I think what I've tended to do is sort of align myself with a reputable company selling these parts into a motorsport application, and they will build up that knowledge from all of their data points with their customers and be able to advise for your application probably at least a good pad to get you started with. So you're not kind of starting blind. You might not have the perfect pad combination, because a lot of this does also come down to driver preference. You might not have the perfect pad combination front and rear, but at least it should have you inside of the ballpark, and then you can start comparing the data sheet of that pad you're running to other data sheets and get a feel of like, if I go this way, what's that going to do for me, and make more educated decisions when it comes to your next set of pads. And I've sort of found that's a pretty good way to get dialed in. It might take a little bit of time and a little bit of money, but at least you're starting inside of the ballpark, which I think is important. Let's move on and talk about another element, which obviously is critical, and I think it's probably the last key element, which is the brake rotor itself. Again, we've kind of talked about bigger not always being better. Obviously, we sort of see with big brake kits, typically, as you mentioned earlier, we're going to end up fitting a rotor that's as big as we can physically fit inside of the wheel. What that is going to end up doing is affecting the distance from the center of rotation that the brake pad is actually clamping on. How does that affect the effectiveness of the braking system?
Yeah, so we call it the effective radius. So it's the kind of middle part of the disc where it kind of passes through the center of all the pistons. And as you run a larger effective radius, you're gaining that kind of moment. So it's kind of like the leverage effect, isn't it? If you're kind of tightening up your wheel nuts and you're trying to do it with a short little wrench, it takes a lot of effort. You kind of extend it and put a large beam on there, and it's an awful lot easier. And it's the same with the brake. The further away from the center that you're applying that pressure, the less pressure you need to apply. Therefore, the less kind of expansion of the caliper, the less fluid, the shorter the brake pedal. So it's kind of an easy win as far as gaining additional brake torque for a given kind of pressure.
So, I mean, it doesn't really sound like there's any downsides there. And probably I'll just mention a concept here that is easy to overlook. We should have probably talked about this earlier when we were talking about braking distances and the other knock-on effects with a big brake packages. Ultimately, the braking package is going to be limited in what it can do. There's no magic here, because really the limiting factor in terms of retardation is the contact patch between the tyre and the racetrack, and then all of the elements around the tyre that you're actually running. So really our aim with the braking system is to get and maintain the retardation right sort of on the point of lockup, essentially. So irrespective of the size of the rotor, the brake pad, coefficient of friction, and all of the other elements we've talked about, really it still comes down to getting and maintaining that braking force right on the point of lockup. And at that point, the braking distance and how quickly the car can slow down is really a factor of the tyre. Is that fair as a statement?
It is. And big brakes, the time that they offer the biggest advantage is when you're at kind of Vmax. So when you first hit the brake pedal and you've got maximum kind of speed, you've got maximum aero, pushing that tyre down into the road, that's when the big brake will kind of really come into its own and be able to kind of shorten that initial stop. As you get to the slower speeds, then you're kind of coming off the brake pedal, and where the kind of advantage then comes in is kind of that confidence and that feel and that repeatability, in the sense that you can retard that pressure and back off and not lock a wheel. So, yeah.
Yeah. In terms of the materials for the brake rotor, I mean, typically we're using a ferrous material in most road cars and, sort of club day race cars. At the higher end, we see sort of other materials such as ceramic or even carbon. Can you talk to us about the differences of those materials and the case study, I guess, for use of materials like carbon for higher end race cars?
Yeah, sure. So, certainly when it comes to kind of ferrous iron discs, then Alcon uses its very own formulated disc alloy. So that kind of will give you an advantage over your standard rotors. It's a more expensive alloy, which is why most factory fit would not look to use that. But obviously iron is still a very high mass, high density material. So as you're kind of looking to save weight, kind of the next option to look at is carbon ceramics. And these kind of really derived from the full-on motorsport applications where they were running carbon, and people trying to transition and gain the benefits of carbon, which is kind of ultimately very low mass, and it's a rotating mass. So it's the most advantageous weight to lose from a vehicle is kind of rotating unsprung mass. So, but carbon just don't work from low temperatures. So they're not suitable for road applications. And this is really where the carbon ceramic then kind of came into its own. It was developed as a means to try and get as close to the carbon weight as possible. So certainly a lot lighter than iron, but still be able to operate from cold. So suitable for road applications. The other advantage with that is, as well as being kind of lighter, you get almost no air from a carbon ceramic disc. Certainly if it's operating within its kind of limit as far as temperature is concerned, then in theory, they could almost last forever. But yeah, they're obviously more expensive, but they are lighter than kind of the iron disc. So the carbon ceramic kind of sit between the iron, which is probably, one of the lower cost options, the carbon, which is one of the most expensive and also not suitable for use, particularly from cold. And yeah, it kind of fills that gap between the two as being a lot lighter than iron, but still being able to operate at extremes of temperatures whilst minimizing that rotating mass as much as possible.
Yeah, and the brake upgrade area is one of those sort of unusual areas of the car where almost everything else we do to reduce weight. But of course, if we take a factory brake package and fit a larger big brake kit, almost certainly with a ferrous rotor, we're going to ultimately be adding weight. And as you mentioned, it's kind of like the worst potential place to be adding weight. It's rotating and it's unsprung. So anything we can do to reduce that while also get the benefits of the big brake kit are obviously beneficial. I mean, particularly the ceramic rotors, as I understand them, cringingly expensive. We see them on a lot of supercars and hypercars as factory fitment, and also requires a reasonable amount of care because they're very fragile and brittle. So if you take a wheel off wrong and knock the inside of the wheel against the rotor, that in itself can be enough to actually shatter or damage the rotor, correct?
Yeah, I mean, they're I would always kind of recommend kind of cares taken with them. They are more fragile than iron discs. They're still very robust in their nature, but yeah, the last thing you want to be doing is kind of chipping a disc, an expensive disc at that, and kind of, having an early end of life due to some external damage occurring. But they are robust. They're not as fragile as carbon for sure, but yeah. There's
levels to this. All right, the next topic when we're talking about rotors is the slotting, if any, on the rotor. And, as we've sort of seen time go by, it used to be pretty common for rotors, and I'm probably primarily talking here ferrous rotors, to be cross-drilled, which kind of had pros and cons. Ultimately, quite often leads to cracking pretty prematurely, which obviously isn't ideal. Now it's more typical to see sort of slotted rotors. So other than kind of looking cool or like it's a race car, what are the actual performance benefits of cross-drilling or slotting on the rotors? What does it do?
Yeah, so you're absolutely right. Cross-drilling has almost been replaced completely with slotting. Cross-training was good. It kind of gave you kind of those edges to kind of clean the pad and cut the pad whilst lightening the rotor to a certain extent, but they did lead to crack propagation from there. So yeah, most things have now moved over to slotting, but the reason that they're there is that they give a kind of cleaning edge to the pad. So they help pads or prevent pads from kind of glazing up. They're given a kind of a wiping, and they can help with kind of initial bite as well. And they also help with kind of preventing the layering of the gassing of the pad that can occur. So as you kind of bed pads, but also as you kind of start to use pads at the extremes of the temperature, they can start to gas off a little bit. And that sits as a layer between the pad and the disc and can kind of be one of the reasons that kind of leads to fade. But by slotting discs, it helps to dissipate that gassing. So yeah, there's a number of reasons that we tend to do kind of slotting, and everybody has a kind of a different style of doing it. But the reason they're there, the function that they're there, probably is pretty consistent across all of them.
Yep. Okay. Fair enough. Got to the bottom of that one. Next element with the rotor is how it's actually attached to the upright or hub assembly. And traditionally with a race rotor, it's going to be attached to a separate alloy hat or mounting plate. And that helps reduce the overall weight of the assembly as opposed to the entire disc being ferrous. But how that's attached, how the alloy hat attaches to the rotor, we can see this being sort of a rigid fixture or floating, where the disc is actually allowed to move. And I mean, I can imagine there's a differential expansion rate between the rotor, which admittedly is going to be exposed to more temperature than the alloy hat. But obviously a ferrous material versus an alloy material, aluminium material, there's going to be a difference in the way they expand. So can you talk to us about rigid mounting versus floating and where the sort of pros and cons are of those techniques?
Yeah, so floating is exactly as you describe. It's a means by which we can drive through the bell to the disc, but allow that thermal expansion, that diametric expansion of the disc, not being constrained by the bell. So it kind of grows within what we call kind of bobbin slots. So you'll typically have 10 or 12 kind of mounting bobbins, which, like I say, allow for the kind of the drive through those, but give you full diametric expansion due to that differential thermal. It's not unusual for a ferrous iron disc to grow 1 or 2 millimeters in diameter through its whole temperature range. And if that was constrained, the stresses that would build up between that joint of the alloy belt and the disc can cause all sorts of kind of coning, odd shapes, even cracking in extreme cases. So we want to kind of allow for that expansion to happen and not try to restrain it. Where you kind of can get away with fixed is usually lower temperature applications. So you may see them at the rear of an application where the temperatures are going to be a lot less. That thermal expansion isn't going to be quite so significant. You sometimes see kind of bells that have kind of saw cuts in them almost. So it's almost like fingers, and that is a way to give some level of kind of expansion without kind of constraining it. So it is all down to that thermal expansion. And, you know, you kind of want to, rather than restrain it, you want to allow it to happen and not allow those stresses to build up.
Yep. Now, another element that sort of, I think, probably feeds into this is pad knockoff or pad knockback, which is, for anyone who's experienced it, a relatively terrifying situation where you come up to a braking zone, hit the brake pedal, and instead of that nice firm pedal with no movement that you're expecting, we get what's referred to as a long pedal where it may travel a significant distance before it actually starts to have any effect. And that's not what you want as a race driver. The element here is sort of, well, actually, let's hear it from you, Steve. What causes pad knockback?
So pad knockback is usually caused by disc deflection, hitting the pad and pushing those pistons back into the caliper. If that then displaces fluid back to the reservoir, that basically means that the next brake apply that you have to do has to displace that fluid back into the system before you're into the braking event. So it gives you that long initial travel, which kind of, you know, takes you by surprise and can kind of feel quite kind of scary for the driver. Disc deflection can kind of occur from, it depends how kind of uprights and wheel bearings and all of that interaction is occurring. It can occur as race cars go over rumble strips. So you're kind of bouncing that wheel and you kind of get some disc deflection, which then knocks into the pad. It can be on high speed cornering where you're getting high cornering G and a disc is kind of deflecting over and pushing the pad. On almost all race cars, we run with really low running clearances, which means that the pads and the pistons are really very close to the disc in order to give us that kind of low initial travel on the brake pedal. So you don't get kind of an initial long travel before you're into the hard pressurization period. And so by running those low clearances does open you up to susceptibility for knockoff. So as brake engineers, one of the challenges that we're always faced with is trying to minimize those running clearances while not actually having an issue with regards to knockoff. And there's a number of ways that we go about trying to mitigate that.
A lot of this really comes down to just the flexibility in the components. And you've kind of mentioned some of those cases where, you know, running a ripple strip or something of that nature, that's going to potentially distort some of the components, which on face value you might think are reasonably stiff. Am I right in assuming, though, that the full floating rotor is going to go some way towards eliminating or reducing the effects of pad knockoff?
It possibly can. The issue you've still got some axial movement on all of the race things. They're not biased in a particular direction. They're free to float. Kind of nominal float for us is about 0.36 of a millimeter. So not very much, but there is some axial movements within that bobbin slot. And so if you've got a disc that's vibrating and wobbling due to having gone over there, then that amount of kind of movement is enough to kind of take up that initial clearance and hit the pad, which in turn pushes pistons back into calipers. So it isn't always necessarily a benefit to run kind of floating in order to overcome that. I'd say that certainly as you run bigger brakes, then the susceptibility to that can be greater as well. So it becomes even more important when you're running big brakes to be conscious of kind of knockoff on what you've done in order to resist that or mitigate against it.
Yeah, absolutely. And I mean, you see that this is something that even in professional series, race drivers are dealing with at some level quite frequently. And if anyone who's watched sort of racing quite closely, you often see the drivers, while they're going down a long straight at high speed, well before they ever get to the braking marker, you'll see the brake lights just come on very briefly. And what that is the driver, he's still at full throttle, and they'll just tap the brake with their left foot. And what they're doing there is first of all, taking up any of that deflection. So getting rid of that long pedal so that when they actually get to the braking point and hit the brakes, they're going to have that immediate braking retardation. And also, I guess just in the back of your mind, it's a bit of a confidence boost that you know that, yep, the brake's still there. When I get to this braking point, the brakes are going to do what I expect. So there's mitigation in that regard. Another element that I've had a very small amount of experience with is anti-knockoff springs, which are a little spring that go in behind the piston, essentially forcing that piston out against the brake pad and therefore the brake pad against the rotor. Have you got any sort of info for us on those springs? Is that still something that has relevance, or have they sort of gone sort of by the by, essentially?
No, that is still something that we still sell. It is still something that is used. We've probably over the years developed kind of the seal grooves and the seal interaction more in order to be able to combat that. And certainly on some of the ultra high end kind of motorsport applications, they also look at quite clever things in the actuation side as well, with valving in order to mitigate against that. But yeah, for your kind of day drivers, if it's something you suffer with, then yeah, anti-knockback springs, conical little springs that sit behind the pistons are still available in order to try and see if that improves the situation for sure.
My fear with that has always been that, I guess to a minor extent, it's kind of like almost dragging your foot very lightly on the brake pedal the whole time. I'd see, and I don't know if I'm completely off the mark here, that those little anti-knockback springs are actually applying some level, albeit hopefully minor, of force against the brake pad and running it against the disc. Is that a consideration? Is it an issue? Does it cause knock-on effects of increased temperatures, or is it not as extreme as I'm sort of picking up?
I mean, we certainly sell different rates of springs. Generally, you know, you always want to be looking to select a spring that doesn't overcome the threshold pressure required or the threshold force to move that piston through the seal. So yeah, if you start to see that you're kind of getting drag, obviously that can affect your top speed. It can also affect the cool down rate between brake applies. So yeah, drag is certainly one of those things that you want to avoid being too excessive for sure.
All right, let's move on to the next topic I'm interested in, which is the brake bedding procedure. And I mean, this is something that pretty much anyone who's changed brakes on a race car's probably gone through. And I think there's a lack of sort of consideration of how important this is and what we're actually trying to achieve during that break-in process. And at least as I understand it, done properly, you're going to have a more effective braking package that's working as intended, and as an upshot as well, even improved life expectancy out of the pad and rotor. Doing it wrong, obviously, kind of the polar opposite of what I just mentioned. So yeah, talk us through the bedding procedure. What is Alcon's sort of recommendation for bedding, and how do we know that we've done it right?
Okay, so yeah, I guess firstly, for those that probably don't kind of understand what's going on in the bedding process, is we're actually transferring a layer of the pad material onto the disc itself. So in normal use, the pad doesn't break against kind of raw cast iron. It breaks against a transfer layer that has been put onto the disc. So in the bedding process, what we're actually looking to do is deposit an even transfer layer of brake pad onto the disc surface, and doing so without introducing any thermal shock into the disc itself. So one of the biggest kind of killers of discs or rotors is thermal shock. So what you want to try and do is look to build up that temperature gradually with gradual brake applies, and not go straight into a full-on, high-speed decel from cold. You want to try and build up those temperatures, and it's all about depositing an even transfer layer across the whole face of the disc. And when it's done right, you can generally see by looking at a disc that you've got that deposition of pad material over the full kind of radial depth of the pad, over the full circumference of the disc, and it looks even and kind of consistent across its appearance. The other thing that I'd always kind of tell people is the last thing you want to be doing is kind of doing a bedding process or even brake applies and then coming to a rest with your foot on the brake, because what you end up doing then is the kind of pad bonds to the kind of disc. You get kind of a very odd heat transfer through the disc and into the pad. And then that can actually kind of tear away and damage that transfer layer, as well as doing damage to the brake system and the rotors themselves.
I mean, I think that point's important almost irrespective of the bedding process. I think most people probably could understand this, but the last thing we want to do is come in from a track session, come into the pits hot, and stop the car stationary with the brakes still at a massively elevated temperature, which is why you kind of see people who are in that situation, generally they'll sort of spend 5 minutes or so rocking the car gently backwards and forwards so that the hot pads aren't constantly in contact with the same area of the rotor. That can help also prevent warping of the rotor, if I'm correct?
Yeah.
All right, so coming back to that bedding procedure, the way, again, there's sort of variations on this depending on the manufacturer, but the way I sort of normally see this done is it'll be maybe 10 to 12 stops, and you'll sort of start, as you mentioned, building up a little bit of initial brake temperature without actually dragging the brakes, no left foot braking here, and then you'll start with maybe 5 of those stops might be sort of 50 or 60% braking force from maybe 100 kilometers an hour down to maybe 20 kilometers an hour, and then as you get sort of further through and sort of get up to 10 and 12 braking applications, you might be sort of up to 85% braking force, again that same 100 down to sort of 10, 20 kilometers an hour, not stationary, and then a sort of a cool down procedure. Does that sort of match your expectation on that process?
Yeah, no, it's a very good description, Andre. Yeah, exactly that.
In terms of, like, often if you've got a dedicated race car, obviously you can't just pop out on the street and bed a new set of pads and rotors on the weekend. Doing this at a track day or a competition meeting can be difficult, sometimes actually dead right dangerous if you've got other cars at pace on the track and you're sort of randomly hitting the brakes where they're not expecting you to. So that's a consideration. But in terms of that process, after you've done that initial sort of 10 to 12 stops, are you good to sort of just send it and get straight into a full 10/10ths race lap, or does the whole system require completely cooling down to ambient temperature before you can go ahead and do that?
No, I think you can. Say the thing that I'd always be mindful of is kind of thermal shock is one of the biggest killers. So actually having some temperature in the brake system when you kind of go pushing hard is always good. I mean, you see people generally on kind of an outlap just getting some temperature into the tires and the brakes, and that is for that very, very reason. Actually, you don't want a thermal shock. The brakes will withstand extremely high temperatures, but what they don't like is going from kind of 0 to 700 in a single stop. So, build up, get some temperature in there, get some bulk mass temperature in there, and then you're good to go.
Another option that I've seen available is sort of pre-bedded rotor and pad combos, and off air we were talking a little bit about that as well. So this is a service that Alcon can offer?
It is. We have 2 dedicated kind of dynos, if you like, for bedding. And we bed pads and rotors, and even for some there's match bedding as well. So a set of pads will get bedded to a disc and kind of serialized accordingly and kind of used. But the general kind of consensus is that, bedded pads, you're kind of going through a level of kind of fade. You're just degassing, you're removing some of those releasing agents during the manufacturing process of those pads. And for rotors, it's exactly what we talked about. It's getting that even, consistent transfer layer. And obviously the benefit of doing it on a dyno is you're not doing it amongst traffic. You can do it in a very controlled way, and you kind of get that kind of out the box kind of bedded product. And then all that leaves you to do then is the kind of warm up kind of cycles just to get some bulk mass, and then you're kind of in it.
I mean, there's a lot to be said for that. I kind of already mentioned a couple of the potential downsides of bedding on the racetrack, but apart from the potential danger of it, you're also likely to lose a session, or at least a good part of a session, which obviously track time is expensive and important. So the pre-bedded, while I have no doubt they come at a price point as well, particularly for professional teams, having the confidence of bolting on a pre-bedded brake and pad package that has been bedded correctly, and being able to essentially hit that first session on the track at maximum effort, obviously bearing in mind building up those temperatures, which you've already mentioned, slowly, that's got to be worth quite a lot, I would imagine. Let's move on, and we probably should have covered this first, but we're actually going to cover it last. We've talked about Alcon, and I kind of felt like maybe Alcon doesn't need too much introduction because it is one of those big brand names that anyone who's been in motorsport, I would imagine, has already heard. But can you give us a quick lay of the land? You sort of mentioned 28 years ago when you joined, there were 30 or 40 staff. I can only imagine it's grown significantly over the time. So current generation, current day, give us a sort of a 30,000 foot view of what Alcon is in terms of the operation, size, location or locations, number of staff, etc., and services offered.
Okay, yeah. So we're probably just shy of 200 people in the UK now. We're based in Tamworth in England, which is pretty much right in the middle of England. At the site at Tamworth, we've just acquired a 4th building, but we have our main manufacturing facility on site. So we manufacture almost all of our components ourselves. We have the design team there, production engineers, purchasing, and then we have a dedicated research and development building that houses an MVH dyno, so something that's very important for our OEM customers.
Could you maybe just explain that term NVH for those who haven't heard of it?
Yeah, so it's noise, vibration and harshness, and it's the kind of level of comfort. So when you're talking about all of the different kind of brake noises, things that aren't quite so significant for race teams are very significant for OEM cars. So, you kind of get your brake squeal, your groans. They've got all sorts of different names to them, and everybody kind of uses slightly different ones to describe it. But it's all about that kind of comfort level of the brake package. So, for our OEM customers, that's equally important as the extreme track day performance that they're able to achieve. So probably for our OEM customers, the range is probably even more significant. When you're doing things for race teams, you kind of know that you're designing a brake package to be used on a racetrack. When you're designing for these kind of hypercars now, then actually they want all of that. Plus they want a level of comfort for driving around the streets. So the range is kind of massive. And to help support that, like I say, we invested in our own dyno. So we're able to put our own brake package quite often mounted onto the customer's upright and hub assembly. And that's in a kind of a quiet chamber. We have full temperature control and humidity control. And that is able to record any noise events. And we can develop kind of solutions to alleviate those noise. So there's an awful lot of work that goes into that level of development. We also have a performance dyno as well, so we can replicate pretty much any racetrack around the world. We can use feedback from ratings in order to be able to look at brake temperatures and reproduce those on the dyno and look at cause and effect and any issues they're having. And also, obviously, we talked about it quite extensively about kind of pad development and understanding different pad behaviors. But also we're forever developing and evolving our products. So we're signing off and testing new products. We're looking at new materials and various different compounds. And we're able to do that all kind of on site ourselves. We also have kind of climatic chambers that can go down to -40. We have hot temperatures. We can take things up to plus 200 degrees in that facility as well.
Right. So really a torture test for everything.
Yes. Yeah, exactly. Yeah. And then we have a dedicated building for assembly as well.
Okay. I mean, it's a big operation, no doubt. I guess this sort of leads on to something that's been on my mind during this conversation. This is a fairly mature industry now. The technology is mature. We know what we're trying to achieve. Where is the innovation left to further improve the braking system on a car? I mean, you kind of alluded just before to materials, etc. But yeah, what's left? I can only assume there's sort of no massive and obvious low-hanging fruit left to pluck, and now you're sort of onto those smaller and less relevant iterative improvements that give sort of a 0.1% improvement rather than 10% improvements at a time.
Yeah, I guess so. I mean, like you say, we're always kind of evolving and looking at improving our processes for kind of the caliper optimization. I think also the customers that we work with, and we work very closely with our customers, their level of their system understanding is kind of second to none. So being able to work very closely to them and design a brake package that meets the requirements is also seeing kind of, step advantages for those guys as well. Also, cars are developing, so either full EVs or even kind of ultra high performance that are kind of hybrid. They kind of have the kind of EV mode or the stealth mode, as some kind of call it. So going back to what we were saying about the MVH side of things, then actually the kind of noise in silent mode when you're running electric motors is kind of even more important. You're less likely to be kind of drowned out by kind of engine noise and things like that. So noise development and understanding our product is kind of forever evolving, and we're forever learning and evolving our product. So yeah, and even with kind of EVs brings a new set of challenges. So certainly in kind of OEM with regen braking and those aspects as well, the brakes are potentially getting used less and less. So corrosion and all of those sorts of things are potentially driving other kind of advances in other materials as well, where you don't need quite so much kind of braking power, but actually non-corrosive, lower mass, lower rotating mass, more lightweight brake packages for OEMs is probably becoming even more important. If they can get the weight of the vehicle down, they either gain range or they gain battery. They can add more batteries due to weight. And so, yeah, we're always kind of being sent in a slightly different direction, or it's set a slightly different challenge based upon kind of the evolution of vehicles as a whole.
Yeah, fair enough. It makes a lot of sense. All right, Steve, it's been an amazing chat and a huge amount of information in here, but we do probably have to get on towards wrapping this thing up, and we'll do that with the same 3 questions we ask all of our guests. So the first of those is what's next in the future for you? Now, I guess we've probably just alluded to some of the direction that Alcon's going. You've been a fixture there for 28 years, so I'm guessing you're probably not on the move anytime soon, but yeah, fill us in. What's going on?
Yeah, I mean, like I say, for me, it's been 28 years, but the industry is always evolving. We work with some of the best customers, the best race teams in the world. And so there's always a challenge around the corner. And that's what kind of keeps me interested as an engineer, is just, that advancement in technology, be it kind of through design or materials or kind of whatever the kind of next kind of challenge is. So that's the thing that always kind of keeps me interested. For as long as that kind of happens, then I'm well and truly Alcon through and through.
Fair. Is there any advice you could give to a younger version of yourself, or maybe one of our listeners, that would help you reach where you've got to today in your career faster, or potentially maybe avoid some pitfalls that you've experienced?
Yeah, I mean, I think the guys and girls that we've kind of employed recently, we've taken on some apprentices and we've taken on some degree graduates. The quality of people coming through at the moment is absolutely fantastic. And I can see a really bright future for all of the guys. And I think hopefully as managers, we kind of are pushing those people and we're trying to grow those people. And I think our desire to kind of do that is what's going to move those on at a pace probably quicker than I did. And then hopefully they take that and they kind of bring people up as well through the business. So I think taking a route of either an apprenticeship or a degree and being prepared to kind of start almost at the bottom. But I think that with a level of dedication and enthusiasm, people shine and people grow. And I can see that with people that have come into Alcon relatively recently, that they've got a really bright future.
So it sounds like you're sort of advocating there in terms of, like, rather than trying to do everything yourself, smart hires and leveraging the talent that is out there to sort of multiply your capabilities rather than just being one person. Is that sort of a rough summary of what you're saying?
Yeah, I think so. And I think actually looking to see how, is there anything else you can do to add to what you're kind of learning? So if there's a night course in CAD, if that's an area you want to explore, even looking to kind of volunteer and help with some of the race teams of a weekend. If there's any way in to kind of get in and get some hands-on experience or develop yourself further beyond what is kind of just laid out in front of you, really going after it and grabbing those opportunities. I think that's the key to kind of,
Yeah. I mean, I think that we've never lived in a time where information was more available, be it freely on YouTube or just generally on the internet, paid courses, our courses, of course, and other training facilities. So if people really genuinely have a desire to learn a skill, the ability to do that has never been easier. And it's the old story, if you want something bad enough, you'll find a way. And if you don't, you'll find an excuse. So I really stand by that. Let's move on to our last question, Steve. And if people want to follow you, see what you're up to, learn more about Alcon, the product, etc., how are they best to do so?
So Alcon has a kind of Facebook page. I think that's probably the best place to kind of keep up to date with kind of what's going on with Alcon, what some of the guys are kind of do. I think that's probably the best route for people. We also have a kind of a website as well, and we put information on there.
Right, well, we'll put links as usual to those resources in the show notes just to make it super easy for everyone to find. Look, it's been a great chat, Steve. Huge amount of information in there that hopefully is going to be beneficial to those listening to expand their knowledge on braking systems and maybe some of the considerations they need to keep in mind if they're upgrading or modifying the braking system. So thanks again for your time today. We really appreciate it.
No, thank you very much indeed. I really appreciate it. It's been really good speaking to you.
Cheers. If you enjoyed this episode of Tuned In with Steve, we'd love it if you could drop a review on your chosen podcasting platform. These reviews really help us to grow our audience, and that in turn helps us to continue to get more high-quality guests. To say thanks, each week we'll be picking a random reviewer and sending them out an HPA t-shirt free of charge anywhere in the world. So this is a great place to ask any questions you might have too, and I'll do my best to answer them if your review gets picked. So this week, a big shout out to Mad Max from Canada, who has said, great talks with knowledge and experienced people from the tuning industry. Andre has a great way to popularize tuning terms, and everyone who listens to these podcasts can have a good time and take advantage of the info he gives. Well, thanks for the kind words there, Mad Max. And if you want to get in touch with us with your t-shirt size and shipping details, we'll fire a fresh tee off straight out to you. All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.